Hi everyone, my name is Justin Cross and this is my submission for Homework 5, the second part of Exam 2 for my Transport 1 class. We see here the question that we were given: for the following network, calculate water flows through each pipe segment and a net flow in and out of the water source and sink nodes. The source node being node 0 and the sink node being node 4. All elevations are at 0 meters except for node 0, which is at 30 meters. Node 4 is fixed at 0 pascals, while node 0 is set to 200,000 pascals. And then the diameters of all pipes are 0.1 meters, and the relative roughness is 0.001 meters. And then the question goes and gives us the pipes, some more pipe information. So it gives us the from node, the to node, the length, and the K value, which takes into account any twists, turns, bends, separations, anything like that. And what I've done here, I have taken that information and I've given us a little illustration so we can better see what's going on. So for example, this first row, the from node is node 0 and the to node is node 1. That's shown here from 0 to 1, and then we're given an L value and a K value right there. And I did that for all of these pipes, and this is just giving us a better understanding of what the question looks like so we can better figure out how to solve it. So from there, we can actually go into Python and we will start coding this out. Now the first thing we want to do is find our imports. So what we're going to use, we're going to use numpy, of course. So import numpy as np. And we're also going to use a couple numerical solvers for this, specifically from scipy.optimize. We're going to use Newton and we're going to use root. So from scipy.optimize, import Newton and root, just like that. All right, what else do we know? We probably want to know what the gravitational constant is, so G. We want to know the density, rho. We want to know the viscosity, mu. And what else do we want to know? We probably want to know the diameters of all the pipes and the relative roughness of all the pipes. All right, so let's fill these in. We know the gravitational constant is 9.81. The question stated that we're working with water, so the density of water is 1e to the 3, while the viscosity is 1e to the minus 3. Minus 3. We were given the diameters of all the pipes, so that's 0.1, and the relative roughness we were given as well, so 0.001. And make sure that's right. Perfect. All right, shift enter, and we get to move on. Now what I've also done, I have found a couple equations that we can use here. So for example, we took the Bernoulli's equation, where we're given a change in pressure, a change in height, and then we're not accounting for change in velocity here, because we're assuming it's all constant velocity. And we set that normally, in the past we set it equal to 0. But now we're accounting for the frictional heating, which is given here. So again, we're taking into account the K values, the length, the diameter, the velocity, the gravitational constant, but we're also taking into account this F, the fanning friction factor. And that actually depends on the Reynolds number and the relative roughness of the pipe. So what we want to do is we want to make a function for the fanning friction factor, and that was actually done for us because it's a pretty big equation. So what I'm going to do is I'm going to copy and paste it from over here, and you'll see how annoying this would have been to write out in real time. So we can see the fanning friction factor. We need to take in a Reynolds number and a relative roughness, and we're going to return the value of the Reynolds number depending on those two values. And again, you can see it's a lot of equation. So I'm glad we're just going to copy and paste it from there. So shift enter, and we get to move on. What's next? We probably want an equation to calculate a delta head, right? So we're going to call that d head. Oops. Define d head. Now, what do we want inside a delta head? Let's take a look at that equation again. We want a K value, the fanning friction factor, the length, the diameter, and the velocity. And then if we look again, the Reynolds number, we need the velocity, but the velocity, we need the flow rate. So what are we going to import into here? We're going to need a flow rate, the lengths, the K values, the diameter, and the relative roughness, right? And what are we going to return? We're going to return this equation here. So I'm actually just going to move this over to my second monitor here so I can just look over and type. So it was a negative k plus 4 times f. What is our function for f? We need the Reynolds number and the relative roughness, ed, and then times L over D, right? L over D, yep. And then multiplied by the velocity squared over 2g, Perfect. Now, what do we have in this return value that we need to calculate? We have our velocity and we have our Reynolds number, right? So our Reynolds number. And then again, if I pull these equations back over, we see we have equations for both of those, for the velocity and for the Reynolds number. So I'm going to type those in here. So velocity was 4 times q divided by pi, and p dot pi times the diameter squared. And then Reynolds number, that's been beaten into our head so many times. That's rho times v times d over u. Perfect. So if we shift enter here and take a broader look at what we just wrote, what we realize, if we look at our Reynolds number, we have a rho value that will always be positive. Our diameter will always be positive, and our mu will always be positive. The velocity right now, as it stands, will not always be positive. But by definition, our Reynolds number always needs to be positive. Therefore, what we need to do is take the absolute value of our velocity so we can calculate the correct Reynolds number. So p dot absolute value of all of this, just to make sure that it stays positive. So our Reynolds number will never be below 0. But what does that mean for our output? What that means is we need to reaccount for the direction of the flow in our output. And we can do that using the sine function in NumPy. So multiplied by np dot sine of our flow, just like that. Perfect. So next we probably, for the problem that we were given, want to find a way to calculate a flow rate. And we're going to use that in another function here. So if we define, we'll call it flow. And to calculate a flow rate, we want a delta head value as well as some of the other parameters we were given. So we'll say delta head, what else? K values, L values, the diameter, and the relative roughness, right? And from here, we're going to return a flow rate. So flow rate. How about we do that? All right. Now this function will actually be our first instance of using a numerical solver in this question. We're going to use the Newton solver where we take two values that we want to equal. We want them to be equal to each other, and we subtract them from each other, and we try to get that difference as close to 0 as possible. So if we take a look at what we want to do, we'll just call this the flow rate. So flow rate, we'll say Newton, and it'll show us what it means. So it wants a function. We'll just call it function for the moment, and x naught, our initial guess for what we want to do, we'll call that the guess. Let me respell function here. So function, perfect. Now, what we're going to do is we're going to write this function. We're also going to find a way to calculate a guess for our initial value, right? So what did we say we want within this function? We want to subtract a given delta head, probably the one at the top of the function. We want to subtract that from a calculated delta head. Probably we can use this equation that we wrote up top. Given a flow rate, we calculated delta head. So let's do that. So we will define a function within our flow function. So we'll define this as function. Now what do we want within this function? We probably want the flow rate, right? If we're calculating a delta head, we want a flow rate. So from here, we're just going to return the calculated flow rate. So d head, and what we're given, we want a q, an L, a K, a diameter, and a relative roughness, perfect, minus delta head, referring to this delta head up top here, right? So what we're doing is we're subtracting one from the other, and we're going to use the numerical solver to get those two as close to each other as possible. And if that happens, the function should equal 0, right? So moving on, what else do we need for this numerical solver work? We need a guess. Well, we know everything when making a guess here. The only thing that we don't know is the fanning friction factor. And what we're going to do is we are going to approximate a value for that fanning friction factor. And we're going to say it's about 0.01. So let's do that here. So we're going to make guess equals, and what we want to guess of is the flow rate. So if we go back to our equations here, we pull those over. Beautiful. What do we have? We have our flow rate is equal to an area times a velocity. And then if we rearrange the second equation here, we get this as a velocity. So we're going to use both of those and make a guess for Q. Again, this fanning friction factor here, we're going to use 0.01. So let's go ahead and do that. I'm going to move that over here. This was an area times a velocity. What did we say the area was? If we look over, it was pi d squared over 4. That's in terms of the diameter. So np dot pi times d squared over 4. Perfect. And what was the velocity? It started with a square root. So np dot square root of negative delta head, let's see, times 2g. So times 2 times g divided by what? It was k. Actually, we can probably just look over here. K plus 4f times L over d. Perfect. There we go. And what do we say we were using as f? Instead of calling that function, it was 0.01. Perfect. So we shift enter here. We actually see something wrong here. Similar to what we saw up here, this Reynolds number had to be a positive number. So does everything underneath the square root, because we're not dealing with imaginary numbers, so everything under a square root has to be positive. And this delta head has this negative sign in front of it. So what do we want to do? We want to take the absolute value. So let's say dh absolute value is going to equal the negative, not the negative, the absolute value of the delta head. Just like that. And then let's replace this negative delta head with dh absolute value. And the same thing here, dh absolute value. There we go. Now you would think this is right. This is actually wrong. I'm sorry. What we need to do, what we need to take into account is the fact that if one of these values equals 0, then the numerical solver will not work correctly. So what do we need to do? We need to take into account that discrepancy. So if we say something like, if the dh absolute value is, say, less than a really, really small number, less than, say, like 1e to the negative 10 or something, then just return 0. Return 0. There we go. So in case this ever happens, it'll just return 0 and it won't say, oh, this didn't work because one of your values equaled 0. So if we shift enter there, and I think we're ready to start plugging in some more of the information that we were given. So let's go back to the problem statement to figure out what information we know. So the first thing we were given here was our information for the pipes. So let's copy and paste that in. Beautiful. Okay. What else were we given? We were given the heights, right? So all elevations are at 0 meters except for node 0, which is at 30. So let's put that in here. So our z. What else were we given? We were told which nodes are external, so node 0 and node 4, as well as the pressures at the external nodes. So external nodes, yep, and external pressure equals. All right, so let's make this an array, and p dot array. what were they? So we said node 0 was at 30 meters, right? So 30, and then 0, 0, 0, and 0. Okay, now which nodes were external? That was nodes 0 and 4. And then what were the pressures at those nodes? Let's make an array of, what was it, 200,000? 200,000 and 0. Beautiful. Now, what else do we want to do here? We probably want to break these this giant array into, you know what, np.array. For some reason that didn't transfer over. There we go. Yeah. So we want to take this giant array and we want to break it into smaller, more digestible pieces. So, for example, we were given this first column is the from node, from nodes, and then 2 nodes. What comes next? The lengths and the k values, right? All right, let's take a look. Let's take a look. So if we want to access just this first column, we can do that pretty easily. We will say pipes of the first column. So bada bing, bada boom. That is all the values in the first column. That's exactly what that will do. So if we copy and paste this down, V, Control V, Control V, beautiful, and just change these values. So 1, 2, and 3, Shift Enter. Everything works. Let's take a look. From nodes 0, 0, 1, 1, 2, 3, 0, 0, 1, 1, 2, 3. Beautiful. So it's working just as intended. What else do we want to know here? We probably want to know the number of pipes we have. So if we take a look at the number of pipes, how are we going to calculate this? Well, each row within this array represents 1 pipe, right? So if we take the shape, the number of rows in each pipe, we can calculate the number of pipes we have. So n pipes equals pipes.shape, and we want the 0th index. So if we take a look, n pipes, we have 6 pipes. 1, 2, 3, 4, 5, 6. Beautiful. Now what we probably want to do as well is find or create lists for the pipe diameters and the pipe relative roughness. So let's do that. So pipe diameter and pipe relative roughness, just like that. What was our pipe diameter? Let's go back over here. The diameter of all pipes is 0.1 meters. So we can use np.full to make a list of all just 0.1 meters. So np.full. What is the shape? The shape is the same number of pipes that we have, so n pipes, and our fill value is diameter, just like that. And let's do the same thing for our relative roughness. Control C, Control V, and instead of the diameter, it's the relative roughness. Beautiful. Shift Enter. Does it work? It works. Awesome. What else do we want to know? We probably want to know the number of nodes that we have. So if we look at n nodes, how would we find that? Well, if we take a look at our array, we see that the maximum node number that we have appears in the 2-node column at the very bottom, right? So if we take the maximum value of the 2-node column, that should give us the number of nodes we have. So if we do np.max of 2 nodes, just like that. Does this work? Let's look at n nodes. 4. And let's actually go back here. How many nodes do we have? 1, 2, 3, 4, 5. Uh-oh. Oh, you know what? We need to add +1 to this because our indexing started at 0. So the first node we had was node 0. The second node we had was node 1 all the way down. So the 5th node we had was node 4, which makes sense why the 4 was there. So now it's 5. Awesome. What else do we want to do here? We probably want to make a list that will hold the values of all the heads that we're going to calculate. So heads, to make an empty list, so np.zeros, not np for numpy. And how long is this list going to be? Well, for each node, we're going to have a number of heads, right? So n nodes. Oops. N nodes. There we go. Float 64 object cannot be inserted. Okay, so we need to change something from a float to an integer. Let's see. And it's probably n nodes right here because it's the thing we're calling. So n nodes, let's say dot as type np dot integer 32. We'll say. Does that work? Oh, that works beautifully. Okay. Now, if we take a look back at our equations, what do we see? What do we see? We see that this first equation here, we can actually calculate delta head using a pressure, a density, gravitational constant, and elevation. Well, if we look at what we know for our external nodes, do we know the pressure? Yeah, it's given right here. Do we know the density? The density for everything's the same? Yes. We know the gravitational constant. It's a constant. Do we know the elevations? Yeah, we know the elevations for everything. So that means we can go ahead and calculate the heads for all of the external nodes. So if we go heads for the external nodes, external nodes equals, let's go back to that equation here. So it's the pressure over rho g plus the elevation. So let's do that. So external, E-X-T-E-R, external P divided by rho divided by g plus the z of the external nodes. Just like that. So now if we look at heads, oops, there we go. So we calculated the head, the value for the head at node 0, and we also calculated the value for the head at node 4, even though it is a value of 0. So what we want to do eventually is calculate the head values for the internal nodes, nodes 1, 2, and 3, and we will use those values to calculate flow rates. There's one other thing I think that we want to put in here, and that is the values for the internal nodes. So we want internal nodes. What are the values for the internal nodes? Well, we know the values of all of the nodes, and we know the values of just the external nodes. So if we subtract the external nodes away from all of the nodes, we should get the internal nodes, right? So we want the range of all the nodes. So n nodes, right? N nodes. Let's take a look at what that says. So the range of n nodes. Let's take a look. Yeah, so a range from 0 to 5. Awesome. And then we will subtract that from the external nodes. So external nodes. Does this work? No. So what we want to do is, I believe we can change these to sets. So if we do that, minus a set of the external nodes. So a set of the external nodes. Does that work? Yes, so internal nodes. Let's take a look. All right, it's a set still of 1, 2, and 3. So we're getting close. We want to convert that back to a list. So a list, just like that. Now if we take a look, boom, it is a list. Awesome. So what do we want to do next? I know. All right, so what we're going to do next is we're going to make 2 more functions. One of them we're going to take into account the, but we're going to use one function to calculate the flows through each pipe. And the next function, we're going to take those flows through each pipe, and we're going to use them to calculate the net flow rate throughout each node, because that's what we wanted to find with this question. So let's define 2 more functions. So define, what do we want? We want to calculate some flow rates. So calculate flow, and we want to calculate net flow rate throughout each node. So calc net q. All right. Well, what do we want to bring in for this flow rate. What do we want to bring in? We probably want to bring in the head values, right? So heads, and that's referring to this list that we created. That's going to hold all the head values. All right, and what are we going to return from this? Probably some flow rates. So flows. Oh, if I can spell it right. So flows, just like that. Now what do we need for the net Q? We need the flows. Flows, flows, if I can spell right. And what do we need to return? Put a colon here. Probably the net flow rate. So we'll say return, yeah, net Q. All right, how are we going to go about this? Well, first thing we're going to do is make an empty list for our flows. So flows equals np dot zeros. How many flows do we have? Same number as pipes. So n pipes, just like that. Well, I can spell it right. That seems to be a recurring thing that I cannot spell. All right. Now, how are we going to calculate each flow? Well, we have an equation for that. We wrote a function for that. So we're going to use that function, and we're going to calculate the flows throughout each pipe, and we're going to return that list that we calculate. So we say we want to iterate through it. So we'll say I in the range of n pipes, just like that. Uh-oh, what did I do? Jesus. There we go. How are we going to do that? Well, we'll say, well, what is our flow? So flow, calling our flow from up above. So what do we need? We need a delta head. So we need a delta head. What else do we need? A k value. We want the specific k value, so k of I. What next? The length at I. The, ooh, delta head KL. Why is it saying relative roughness right now? It should be the diameter. Li. Okay, I'm just going to go with it. Pipe diameter at I. Oops. And then pipe relative roughness at I. Just like that. So, yeah, and that's going to equal our flows at I. So flows at I, just like that. And what that's going to do is for each pipe that we have, it's going to go through. It's going to find its K value, its L value, its diameter, its what is that? I'm sorry. It's been a long day. Its relative roughness. There we go. As well as its delta head, and it will calculate the flow for that pipe. And then it's going to iterate through that for the same number of pipes that we have, and it's going to put it into our flows list, and that's what we're going to return. All right, so we're missing one last thing in here, I believe, and that is the delta head value. Well, how are we going to calculate that? Well, at some point we're going to know all of the head values. We're going to iterate through all of this, so it's going to get closer and closer to the real value. So what do we want to do? We want to make something. We want to make a delta head value. We actually already used that. Let's just make this h a lowercase. How about we? So our delta head is our change in head. So all of the head going in minus all of the head coming out should equal our delta head. So we will say that equals the heads from the two nodes at I minus the heads from the from nodes at I. And what that's basically saying is, I should probably put that inside the for loop, just like that. And we'll say, fix that as well. This is basically saying, hey, I want to find the delta head for this value. How am I going to do that? I'm going to take the head going into this node, I'm going to take the head going in, I'm going to subtract it from the head coming out, and that'll give me the change in head. And then from that change in head, or delta head, we can calculate the flow. So that's how we're going to calculate the flow rates. Now, what about the net Q? Well, what we know is for each node, all of the flow going in minus all the flow coming out is the net flow. So let's get started here. Give myself some more room here. Let's see, let's make another empty list. So np.zeros. How long is it going to be? It's going to be n nodes long. Perfect. Now how are we going to do this? We're going to use add at. So np.add.at. And how does this work? Well, let's take a look. Well, first it wants A. What's A? What is A for us? A is the list that we're trying to affect. So what is that list? Net Q. What does it want next? And indices? What are the indices that we are trying to find? Those indices are, give me a moment to think here. The indices are probably, let's try this, 2 node, right? So, does that make sense? Does that make sense? Let's try it anyways. And then, what are we adding? The flows. Flows, right? And then np.add.at. What is next? So the same list, so net Q. The indices is from nodes, and the, let me fix that before I go searching for it again. And then what are we adding? The negative flows, just like that. Now, why is one positive and one is negative? It's because we're going into a node, hence the 2 node. Okay, that does actually make sense. So going into a node, using the 2 node, the flow is positive, right? So, and then pulling out of a node, the from node, the flow is negative. So that should work. So if we shift enter, all right. So what do we want to do next? So we're getting close to being able to use the second numerical solver that we imported, the root solver. So let's write this down right now. So if we look at root, what does root even want first? So it wants a function. We'll just put a placeholder there first. So placeholder. And what else does it want? It also wants a starting guess. So just put guess there for now. So what do we want for our starting function? Well, we want a way to incorporate these last 2 functions that we wrote for calculating flow and calculating the net Q. So how are we going to do that? Well, what we want to do, similar to what we did for the external nodes where we calculated the heads knowing the pressure, what we want to do is calculate the heads for the internal nodes knowing the pressure of the internal nodes. But that's the thing, we don't know the pressure of the internal nodes. That's where the numerical solver comes in, where we're going to give it a guess for the internal pressure of the internal nodes, and the root solver will do its thing, and it'll spit out what it believes to be the pressures of the internal nodes. So let's take a look. So the first thing we want to do is make a function that will incorporate these 2 functions, this net Q and this calculate flow. So what are we going to call that? Let's call that net Q internal. So finding the net flows of all the internal nodes. And what does net Q internal need? It probably needs a pressure. So we'll call that internal P. All right. What do we want to do within this net Q internal? Well, what we want to do is calculate the head value for the internal nodes. Similar to what we did up, let's find it up here. Where was this? Where was this? It was here. The heads of the internal nodes. So let's copy and paste this over and replace all of the external with internal. So external becomes internal, external, this becomes internal, and external becomes internal nodes. Just like that. All right. So because it's the same calculation, we're finding the head. It's the same thing. It's the pressure over the density times G plus the change in height. So that's what we want to do. And what are we going to return here? So we're going to return, well, we want only for the internal nodes. So we'll start with there, internal nodes. We want to find the net Q. So thankfully, we just wrote a function for that. So if we go calc, calc net Q, what does the net Q need? It needs flows. Well, we actually just wrote a function for the flows as well. So calc net Q, we take calc flows, just like that, flows. And what does calc flows need? It needs some heads. Heads, just like that, boom, and just of the internal nodes. Beautiful. All right. So now that we have our function that we're going to put in the root solver. So let's put this in net Q internal, just like that. We need to make some guesses for the internal pressures, right? So how are we going to do that? Let's make an internal P guess. What is our internal P guess? Well, we can take the delta head equation and rearrange it a little bit, and we get the head minus z. I'm just going to write this out in, I don't want to call it English, but it's not code. Head minus z times rho times g. Just like that. Now, this z, well, we have the z value, so we'll say z of the internal nodes, just like that. Now, what is this head? We don't know. That's another guess that we have to make. So let's say something like internal head guess. Just like that. Now, since we just defined that, we need to make a guess for that as well. So I'll copy and paste that over. Now, what do we want to use as a guess for the internal head? Well, we know the heads of the external pressures, and it's safe to assume that it's going to be somewhere in between the maximum, well, the head at the top and the head at the bottom. So if we take an average of the two, we should be able to make a pretty good guess of what the head is going to be. So let's do that. So the mean, np dot mean of the heads at the external nodes. Just like that. Does it work? Yes. Now we can plug in our P guess. So internal P guess. We plug that into our root solver and we pray that it works. All right, net Q defined is not defined. Well, that's easy enough to define. Let's make sure I spelled it right. Yeah. Calc flows is not defined. Did we just define that? We defined calc flow. Let's fix that. Do you run? You do not run. Let's find out why you do not run. So the heads of the two nodes saying the problem is here. Only integers, slices, ellipses. Heads of the two nodes and heads of the from nodes. Let's see here. Yep. You know what? These probably need to be integers as well. So dot as type np dot integer 32. Let's put that in parentheses as well, just like that. And the same thing for this. That dot as type np dot integer 32. And once again, we pray that this runs. DH absolute value is not defined. That's because it's a capital, right? DH absolute value. Oh, you know what? We never accounted for that absolute value sign in the return. So what is this flow rate? This is the flow rate multiplied by the sign of the original delta head, right? Because we took the absolute values just to make sure everything inside the square root is positive, we need to reaccount for the sign. Just like that. And then third time's a charm, maybe? Oh, we've got this backwards. So let's copy and paste that over, just like that. So it's defined before it's used. Fourth time's a charm. To node is not defined. Sure it is. Instead of to node, how about two nodes? We're just catching all of my slip-ups, aren't we? Oh, it's beautiful. So what we just did was we calculated the internal pressures of node 1, node 2, and node 3. Oh, that is the beauty of numerical solvers. So what we can do here is say result equals, and make it a variable, and then look at result.x. And there we go. That right there gives us the pressure at 1, the pressure at 2, and the pressure at 3 for nodes 1, nodes 2, and nodes 3. So let us go and start displaying the information in a way that is readable. Now, sorry about that. It was getting a little dark, so I had to turn on my light. Where were we? All right. We were about to display all the information that we just got, right? So let's see what the question was wanting in the first place. We wanted the water flows through each pipe segment and the net flow in and out of the source and sink. All right, that'll actually be pretty easy to do. So what are we going to do? We are going to start with the flows through each pipe. So how do we calculate that? We have a function for that. It's right up here, right? Calc flow. So we're going to use that calc flow. So calculated flows, let's say calculated flows. We'll say that's equal to calc flow of what? Well, we already just calculated all the heads, right? Heads. So actually, let's take a look at what that looks like. So heads, beforehand, we had seen that we already calculated the heads for the node 0 and node 4, right? Because we knew those pressures, but we didn't know the pressures for the internal nodes. Now that we do, after going through that numerical solver, we can finally calculate the flows, or the heads, for those internal nodes, because we now know the pressure. So let's get rid of that here. And let's look at our calculated flows. Calculated flows. Calculated flows. What does this look like? Butterfingers. There. So this basically tells us, oh, this is a calculated flow through the first pipe that we looked at. So if we go and take a look at that, this pipe right here, from 0 to 1. And then from 0 to 2, the flow is this, so on and so forth. So we can iterate through each pipe and show which pipe, or which node it was coming from, which node it was going to, and the flow through that pipe. So how do we do that? We use a for loop, right? So for I in range of, we want the number of pipes, right? So n pipes. We're going to make a print statement. It's pretty basic. So we want a from, a to, a to, and a flow. Oops. There we go. All right. So where is it coming from? We want the from nodes at I. The to, we want the to nodes at I. And the flow, we want the calculated flows at I. Let's see if this runs. Uh-oh. Aha. Let's fix that. Beautiful. Let's fix my typo again. Yep, so from 0 to 1, the flow is this. From 0 to 2, the flow is below that. And then so on and so forth. Beautiful. All right, what was next? What else did it want? The net flow in and out of the source and sink. All right, let's do that. So what's next? We want the net flow. We're going to display the pressure as well, just to make it a little more holistic. So we want to find the calculated net flows. So calculated net Q. And again, we have a function for this. So calc net Q of calc flow of the heads again. Bada bing, bada boom. If we look at that, so calculated net Q, let's take a look. And there we go. So we've got an inlet flow at node 0. That makes sense because it's the source. Nodes 1, 2, and 3 have a net flow of basically 0, which makes sense because they're not they're internal, they're not external. And then again, the net flow out of the sink at node 4 is going to equal this the flow in, which is perfect because that obeys the conservation of mass. All right. So we also want to display the pressure. So let's make a blank list for that. We'll call that pressures equals the zeros. How many pressures do we have? We have one per each node. So nodes and nodes. So the pressures of the external nodes, those are actually given to us. So we will call that the pressures at the external nodes, my bad, is just the external P, which we were given from the problem statement. Now the pressures of the internal nodes equals our result up here, these three values right here. So results.x, just like that. Now let's take a look at pressures. There we go. So as we stated beforehand, the pressure at the source was 200,000 pascals and the pressure at the sink was 0. And then the three calculated pressures fall into place right there. All right, let's do another print statement here. So again, we're going to iterate through for I in the range of n nodes this time. We want to print, and let's do a very similar thing here. So what do we want? What do we want? We want the node, we want the pressure, and we want, let's put the elevation as well. So elevation, and finally we want the net flow. All right, let's fill these in. So the node is just I, right? The pressure is going to be the pressure, S-U-R-E, at I. Z is going to be the Z at I. And the net flow is going to equal the calculated net Q at I. And that, let's see. Oh, yep. More Butterfingers, huh? Oh, we messed up again, huh? EOL while scanning string literal. So the node, our little curly brackets aren't working. Why not? That? Because it was working up here, right? F. Let's see. If we copy and paste what we have up here and then just edit that, will it work? So let's try that. Oh, you know what? We were just forgetting that last bracket. F string empty expression not allowed. What? It's not empty. Let's take a deeper look at this. I think what I'm going to do, I'm just going to copy and paste this print statement from up here and put it down here. So instead of from, we want the node, right? Instead of the 2, we want the pressure. Instead of the flow, we'll say Z. And then we want one more, which was the net Q, just like that, right? And instead of from nodes, we just want I, like so. The pressure, we want the pressure at I. The Z, we want the elevation. And the net Q, we want the calculated net Q at I. Does this work? Pressure, pressures. Ah, there we go. All right, so as you can see now, we're given node 0, the pressure, the elevation, and the net flow. This one is just out because it's a source. And then node 4, we're given the pressure, the elevation, and the flow in, which is exactly what the question asked us to do.